Welcome. In this lecture, we're going to look at solving the least squares problem using principles from geometry. So our objectives are to develop a condition for the solution that's called the orthogonality condition. And we'll use this orthogonality condition to find the solutions to the least squares problem. And along the way, we'll have to introduce the idea of matrix inversion. Now recall that the least squares problem in a machine learning context is formulated as shown here. We have n feature vectors, x1, x2 through xn transpose, and these are p-dimensional vectors, and the inner product of each feature vector with a vector of model parameters, w1 through wp, is supposed to produce a label. Now that label could mean a variety of things. It could be the class that a particular feature vector is associated with in the context of data fitting, a measured data point. So this suggests we're trying to solve a problem AW equals D, where A is this matrix composed of the feature vectors. So A is going to be an n by p matrix. The case we're going to consider has n greater than or equal to p. In other words, the number of feature vectors is greater than or equal to the number of model parameters. And this is frequently the case in machine learning problems. So W is a p by 1 vector, and when I multiply an n by p matrix into a p by 1 vector, I get an n by 1 vector D. Now a further assumption we're going to make is that the rank of the matrix A is equal to p. Now these assumptions will allow us to solve the problem, and we'll later look at ways of relaxing these assumptions with more advanced techniques. So our goal in the least squares problem is to minimize the Euclidean norm squared of the difference between AW and D. So if we define D hat as A times W, we know that D hat lies in the p-dimensional subspace spanned by the columns of A. So we're trying to find a W that gives us the vector in this p-dimensional subspace D hat, which is closest to D in the sense of Euclidean distance. Now let's look at some simple geometry in the case where p is 1, trying to solve for one parameter, and n is 2. This is nice because we can draw it. So let's suppose that A is 1, 1, so that's a 2 by 1 vector. D is 0.5, 1.2, just for illustration. So if I look at D hat, which is A times W, W is going to be a scalar in this case. At D hat, it's going to be W, W. So any vector D hat is going to lie along this line that has slope 1. This line is a set of all points of the 1, 1 vector times a constant W. Now if I look at the difference between my desired D and my D hat, it's this vector that I've drawn in here, and the question is, how do we choose W to minimize that distance? So remember, we're going to be traveling along this line someplace, and we want to find the W that gives us a D hat which is closest to D. So here's our distance. As I go in this direction, of course, the distance increases. If I go out here, the distance also increases. And clearly the closest point is right about in here, where the difference between D hat and D is orthogonal to the line associated with the span of A. So we see that our solution has to satisfy D hat minus D is orthogonal to A. We can look at this principle of orthogonality in three-dimensional space when P is equal to 2, when I have two model parameters. Now in this case, A is going to have two columns, and D hat is going to be constrained to lie in the span of these two columns. And we've seen before that if I look at the space spanned by any two columns in 3 space, that's going to be a plane. So I've sketched this plane in the medium blue color here. D is some vector that lies in general not in the plane, and D hat, which is A times W, that's a weighted combination of these two vectors, it's going to have to lie in the plane. So we're going to try to find the vector D hat in the plane, which is closest to this vector D that in general lies out of the plane. As we look at all the points in this plane that we could choose as candidates, the one that is closest is going to have an error D hat minus D, which is orthogonal to the plane. So this tells us that D hat minus D has to be orthogonal to the span of these two vectors, A1 and A2. Remember, orthogonality meant that inner products were 0, and the inner product of A1 with d hat minus d has to be 0. Similarly, since this also has to be orthogonal to A2, then A2 transpose d hat minus d must also be 0. And if I'm orthogonal to A1 and A2, I'll be orthogonal to every point in this plane. So it's difficult to visualize in more than 3 dimensions, but in general, you can show that the error has to be orthogonal to the space spanned by the columns of A. In other words, the matrix A transpose, because that's going to include both A1, A2, A3, and so on, A transpose times d hat minus d has to be equal to 0. And this is called the orthogonality condition. Whatever we choose for W has to satisfy this condition. So a little bit of matrix algebra will allow us to find W using this condition. So we're going to rewrite A transpose d hat minus d as A transpose times the quantity AW minus d being equal to 0. Well, this implies that A transpose A times W is equal to A transpose D. Now, the nice thing about A transpose A is that this will always be a square matrix. It's going to be a P by P matrix. Remember, A transpose is P by N, A is N by P, so A transpose A is P by P. Now, if we can find an inverse for this matrix and multiply this equation on the left by that inverse and on the right by that inverse, we can isolate W. And that's exactly what we're doing down below. We're multiplying on the left by A transpose A quantity inverse, and then on the right by A transpose A quantity inverse, and assuming that we have an inverse, in other words, this product is equal to the identity matrix, then we're going to solve for W and find that it has to be equal to A transpose A inverse times A transpose D. So this orthogonality condition leads to a very simple algebraic solution for W. So let's talk a little bit about matrix inversion. In general, if B is a P by P invertible matrix, then B inverse satisfies the following. B inverse times B is equal to the identity. Remember, the identity is a matrix which has 1 on the diagonal and zeros everywhere else. And the reason this is called an identity matrix is because if I take the identity and I multiply it times any vector V, I will get the same vector back. So if I multiply on the left by B inverse, I recover the identity. Well, it turns out that you can also multiply this equation on the right by B inverse and get the identity. So let's take a couple simple examples. So if B is this 2 by 2 matrix with 1, 1, 1, 2, then B inverse 2 minus 1 minus 1, 2, and you can check this out. If I multiply B times B inverse, I've got 1 times 2 plus 1 times minus 1. Well, that'll give me 1, which is what I have here. Then 1 times minus 1 plus 1 times 1 gives me 0. 1 times 2 plus 2 times minus 1 gives me 0. And 1 times minus 1 plus 2 times 1 gives me 1. So this satisfies that condition. In general, if we have a 2 by 2 matrix and it has entries A, B, C, D, you can show that B inverse is AD minus BC times D minus C minus B and A. And you can verify this by multiplying B times B inverse, A times D plus B times minus C. I get this term, which is canceled by the AD minus BC in the denominator, so I'd have a 1 here. You can check the other ones out, they work also. In general, closed form expressions for matrix inverses are very difficult to find, and we're going to do that with the computer. Most all software packages have a matrix inverse function, which you give it a matrix and it'll spit out the inverse, assuming the inverse exists. Because not all matrices have inverses, if we try to apply this formula for the general case of a 2 by 2 matrix inverse to a matrix B, which has 1, 1, 1, 1, you see that B inverse in this term here, I have 1 over 0, and that's going to be a problem. And in fact, this matrix is a rank 1 matrix. All full rank square matrices are invertible. So a P by P matrix that is rank P is going to be invertible. And I've got a proof of that in the notes that accompany this lecture. Now there are a number of situations which one can show that matrices are guaranteed to be invertible. For example, in our case, we're interested in A transpose A and inverting that matrix. And that turns out to be an invertible matrix if and only if our matrix A, remember it was n by P and P was less than or equal to n, is a rank P matrix. And there's a proof of that in the notes that accompany the lecture. It turns out that matrices which are positive definite are also guaranteed to be invertible. Now a square matrix Q is said to be positive definite, and we'll sometimes write Q greater than 0, if and only if V transpose Q times V, so V is some vector, is greater than 0 for all vectors V not equal to 0. And that's why we say that this matrix is positive definite, because for any vector V, we get a positive quantity when we do this quadratic V transpose QV. Now this sort of quadratic is present in the least squares problem, and we'll explore that in a future lecture. The proof of this result is also in the notes. So let's show that A transpose A is a positive definite matrix, and therefore, by this property, A transpose A would be invertible. We've already assumed that A is a rank P matrix, so the first property we pointed out is going to guarantee that A transpose A is invertible as well. So the way to show that A transpose A is positive definite is to define a vector Y, which is A times V. Because A has rank P, then those columns of A are linearly independent, and therefore, as long as V is non-zero, Y is guaranteed to be non-zero. So if I look at A transpose A, and this condition where I'm considering Q to be equal to A transpose A, I have to construct V transpose QV. So I'm going to do that by writing this as AV quantity transpose times AV. Now recall that when we have the product of two matrices, or a matrix and a vector, and we take the transpose, it's the transpose of the individual terms in reverse order. So this is going to give me V transpose A transpose times AV. So we have our matrix in the middle here that we're trying to show it's positive definite. And the question is whether this quantity is greater than 0 for any V not equal to 0. Well, from where we started, this quantity is exactly Y transpose Y. And that's Y's inner product with itself, which is the sum of the squares of the elements in Y. Since Y is guaranteed to be non-zero whenever V is non-zero, then the sum of the squares of the elements is going to be greater than 0. And therefore, A transpose A is a positive definite matrix, and by this result, we have that A transpose A inverse exists. Now, just by way of terminology, we say that a matrix Q is positive semi-definite if and only if V transpose QV is greater than or equal to 0 for all V not equal to 0. So we've introduced a number of new concepts in this lecture, and let's just back up and summarize where we stand. We started off considering the least squares problem, where I'm trying to find W to minimize the Euclidean distance between AW and D. And that's equivalent to minimizing over W this error vector E, where we've drawn the error as D hat minus D. So D hat is AW. That's a vector that has to lie in the span of the columns of A. D is some arbitrary vector, and so we're interested in minimizing the length of this error between this arbitrary vector and a vector that's in the space but spanned by the columns of A. And the smallest error is going to happen when we have orthogonality between the error and the span of A. So we use this orthogonality principle that E has to be orthogonal to the span of the columns of A. In other words, A transpose E has to be equal to 0. And we can write that out in a graphical form. So here I have A transpose, and that's a P by N matrix. And then E is AW minus D, and A is N by P, times W, which is P by 1, minus D, which is N by 1, equals 0. So again, checking dimensions, A times W will be an n by 1 vector, and D is an n by 1 vector, so I can subtract these two, and this will multiply into A transpose, which has n columns. Now if I bring this A transpose inside this parentheses, I have A transpose A, which is a P by P matrix, and so I have a P by P matrix times W, which is a P by 1 vector. When I look at A transpose times D, that's also going to be a P by 1 vector. And since the matrix A transpose A is invertible, we can multiply by the inverse of this matrix on both sides of this equation and obtain that W is equal to A transpose A inverse times A transpose D. And this tells us that D hat, the vector that's in the span of A, which is the closest vector to D that we can find in the span of A, takes the form A times W, which is A times A transpose A quantity inverse, A transpose D. So recall we started with AW, trying to isolate W to find out what W is. This process of getting the solution first multiplied AW by A transpose, and then multiplied it by A transpose A quantity inverse. So I'm going to group those two, A transpose A quantity inverse times A transpose, and I'm multiplying that matrix, which is a P by N matrix. Recall A transpose is P by N, and A transpose A inverse is P by P. You can see that when I multiply these things together, I have A transpose A quantity inverse times A transpose A, and that isolates W. And it's a direct consequence of the orthogonality condition.